So I thought that there was a problem, but in reality there is no problem because I print the activation before calling the sigmoid function, so everything is okay. Just erase this line and run this. Once I give an input, I get an output. Let's try it with a more complex neural network. Let's say it has two inputs, two neurons on the hidden layer and two neurons on the output. Let's call it with the vector 1, 1 to see what happens. And after some computation, I get here the output. This is my neural network. And here is the output. So this is the output of my neural network. Let's ask it to have an output of 1. Oh, wonderful. So right now I have a neural network structure with a feed-forward function that computes the output once given the input. Now we would like this neural network to learn some kind of patterns given a set of inputs. It would be nice to be able to learn. The neural network we are working right now has great difficulties to learn because we don't have bias. So I will ask you to add bias here. In any case, I will compute the correction on all the weights such that the neural network learns. Yeah, and to compute this correction, what we need is this. Let's go here. There we are. There we are. So once I get an output, clearly this output is a function. Let's call this weight 1, 1 on layer 1, weight 1, 2 on layer 1, weight 1, 3 on layer 1, weight 2, 1 on layer 1, weight 1, 2 on layer 1, weight 1, 2, 2 on layer 1, and weight 2, 3 on layer 1. And let's call this weight 1, 1 on layer 2, weight 2, 1 on layer 2, and weight 3, 1 on layer 2. So the output is clearly a function of weight 1, 1 on layer 1, weight 1, 2 on layer 1, weight 1, 3 on layer 1, weight 2, 1 on layer 1, and so on, all the weight of the network. So the output depends on all the weight of the network. Suppose we compute an error. So we expect some output and we get another output. The error is equal to the square root of output, the sum from I equal to 1 to n, number of outputs, expected I minus output I square. This is a standard norm of two vectors. If the vectors has just one output, like in this case, I only have one output in this case, it's just the absolute value of the difference. So the error is a function of the output, and the output is a function of the weights. So if I want to know how the error changes when one weight changes, I have to compute derivative of error with respect to any of these weights. This is the gradient of the error when I change this weight. It means if you go for a positive value, you are going for bigger errors. If you get a negative, if you put a negative value, you get smaller errors. So, in reality, this is the derivative of this function with respect to O multiplied by derivative of the output with respect to the weight. And derivative of this function is 1 divided by 2 times the error. Yeah. Multiply it by 2 times the expected value minus the output square. Oop. Multiply it by the derivative of the output, derivative of omega ij. So this is really easy to compute. This is really easy to compute. This two and this two goes out. So I get expected minus output at the E divided by the error, multiply it by derivative of the output E with respect to the weight ij. This is the hard part to compute. Usually people use backpropagation algorithms to compute this, but we are going to make a trick here. Last day I explained you how to compute complex derivative function. It's quite easy. If I want to compute the output, the derivative of this output with respect any weight, the only thing I have to do is to get that weight. For instance, let's take this one. And instead of giving weight 131, I will give weight 131 plus h. H is a small number, j. J is the complex number. So in this way, I get as an output a complex number. And the derivative of output with respect to this weight is just the imaginary part of the output of all the weights, weight EJL plus HJ divided by H. So it's really easy to compute this derivative. It's not optimal, it's slow, but it's really easy to compute using this technique. So what we are going to do is to compute the derivatives of the error like this. And once we have how the error changes as we change the weight, that's the gradient. The gradient always goes uphill. We are going to update the weights such that the error gets smaller. So for each weight in layers, we are going to compute the derivative. We are going to compute the error. And we are going to update the weight. And the way to update the weight will be weight k plus 1 is equal to weight k and minus xi minus xo divided by error multiplied by derivative of oi. This will be my update function. So in this way I update the errors. Let's try that. Here we are. This is myself. let's compute define update will get as a first parameter the expected value of the output. As a second parameter, we'll get the input to the neural network. So this input, I expect that gave me this output. It will get also the net that I'm trying to update. And if nothing, okay, this non-exponential here. Non-exponential here. So let's see how we do this. Let's create h is equal to, for instance, 1 exponential minus 4. You can choose a small number here, as small as you want, yeah, up to the precision of your computer, up to the precision of your computer. So let's make a trick. I don't want, this is a list, and the list is a mutable object. If I start updating values, the neural network will be half updated while updating the rest of values. So in order to keep fix the neural network at the input, what I will do, I will make a copy of the neural network, and I will call it base is equal. But if I do this net, it will be a soft copy, a pointer to the original network. So I probably can do dot copy, but this is not going to copy every list of every element. So there is a nice package in Python which is called copy. Import copy. And here I'm going to the copy.deep copy of net. Now this makes a exact copy of my network. It will be in base. If I modify base, net won't be modified. This is wonderful. Yeah. So now I have a copy. Now I can update the weight of net while using base. Okay, let's go for each weight computing the derivative. So for k layer in enume base. So this will go for all the layers of base, and I will also get an index. This index is nice and important. Okay, let's go ahead. For kk weights, I said weight before in the forward, neuron weight. Neuron weight in layer. Now I'm going for every neuron in every layer. Now for KKK wave in neuron wave. Now I'm going through each wave of each neuron of each layer of the network, and at this point I will make a copy of the base neural network. Net3 will be a copy dot deep copy of the base. And now in this special neural network, net-c, and I will get the layer k. the neuron KK, the weight KKK, this weight, and I will make it complex plus HJ. Now I have a complex weight here. Now net-t has exactly the same weight as net, but one of those weights is complex. So I make a forward on the net C to see the output, and the complex part of the output will be the derivative of the output with respect to. Yeah, but let's make it really as expected. Let's create a function which will be called error function. Define error. Error takes two values, expected and predicted. And this function just says for a1, a2, and zip, expected, predicted, n is equal to n plus a1 minus a2 square power to 2. And once finished, return cmath, yeah, dot sqrt. I could use the brick of the function, but this function will be called only when updating, so it must be the complex one of n. So in this way I get the error. So let's compute the predicted value of the network is equal to forward. Let's put here inputs. Let's put here forward function, the network, net complex, the complex net, and I want to compute this with complex exponentials because I'm going to use complex values. Cmath dot exp. Here we are. So I get the predicted value. Here I get the predicted value. Now I'm going to compute the error. Error is equal expected, comma, predicted. Now I get an error which is a complex number, and the imaginary part of the complex number is the derivative of the error with respect to the weight. And now I'm going to update the weight of the original neural network. Net k KK is equal to the same value minus 1 divided by the error multiply it by expected minus predicted I'm thinking there are multiple outputs, so I should do it for each output. I think if I want to do it for each output or just considering one output. Yeah, I'm going to do it for each output. For let me just a moment to think on this. For element in predicted. It will be this multiplied by, no, this should be in zip expected predicted. Expected predicted. Expected minus predicted multiplier. Take care. This prediction has real and imaginary part, and we don't want to. Oh, yeah. It should be here. Oh. How does the error vary when I change this way? Derivative oh, I'm using complex derivative. Man, I don't need all this stuff. I'm sorry. It's already contemplated in the complex derivative. The complex derivative, I just need the error. Also, I don't need this derivative. It's already contemplated here. So minus then error divided by h. That's the derivative of the error given these inputs with respect to the weight. Yeah. That's it. Yeah. So here the maths are nice to be familiar with the maths, but this is not a course on maths, it's a course on Python. So I really want you to understand the list, the layers, how do you compute the output, and so on. So don't pay too much attention to how you implement exactly this problem. Yeah. The important thing is that you are accessing the structures in the right way. The important thing is that you are able to create the structures to solve a problem. Yeah, because this is Python course. So there we are. So let's make an experiment. Let's say we want a neural network. Here we are, and let's say I want to update the weights. So I will call update, and let's say I know that for the input 1 I should get an output which should be 0.5 on this neural network. So I have the original neural network here. At some point you update that neural network. You don't need to return anything. This is a mutable object, and I get a new neural network. Print neural network, and this is a nice structure. So let's say if I get an update on the values, Probably it's going to crash. This has been a long time since last time I just executed, so let's see what happens. Oh, name base is not defined. Okay, base. Okay, what else? What else? Name J is not defined. It's not J, it's 1J. A complex number, 1J. Oh, to play as an attribute image. This is online. Error here. Error here. Error comes from here. Expected minus predicted. Oh, wow. Error is equal to error expected minus predicted. That's it. There we are. So originally we have this neural network. It comes from this bracket to this bracket. Yeah, this is the original neural network. As you can see, let's make it not so small, like this. No, a little bit smaller. A little bit smaller. That's it. No, just a little bit smaller. There we are. So here we have two inputs, two neurons on the hidden layer, and one output. So here is our network. It comes from here to here. It says it has one layer of two inputs, one layer of two hidden networks, and one layer of outputs. Yeah, and this is the original neural network, and this is the updated neural network. Yeah, so you see the first coefficient has changed a little bit, the second coefficient almost nothing, the third coefficient a little bit, yeah, and so on. So I did an update on the coefficients of the on the neural network such that the error gets smaller. How much smaller is getting the error? Let's try to see how much. So forward 1 neural network. This is prediction, and the error here, here is error expected. Wow, man, what's going on here? Come on. This is predicted forward. The error is equal to error. I was expecting 0.5 and I got predicted. So I update the neural network. Let's avoid printing this. I update the neural network and I compute again the error. And let's see what happens. I'm going to print the error before and the error after the update. Print error. Print error. That's it. So at the beginning it was 0.18 as error, and after update it was 0.13, so the error is smaller than before. So we can create a bunch of numbers. I will ask you to let's I will ask you to create a bunch of numbers let's say numbers between 1 and 1. So if the number is in this sector, the expected value of the output of the neural network should be 0. If the number is in this sector, the expected value of the neural network output of the neural network should be 0. If the number is in this sector, it should be 1, and if the number is in this sector, it should be 1. Yeah. So you create a function in Python. This function creates random pairs of numbers. Here. For each random pair of numbers, you know which is the expected value. So you create a set of data. The set of data will be number 1, x, xy, xy. It will be x, y, and also the expected value 0 or 1, 0 or 1, depending if your number is in a 0 zone or a 1 zone. You create a list x does y2 1 x3 y3 0 and so on. You have to create a function to do this. So you create 100 of values, you know each classification, and you use this classification to train the neural network. Once you have trained the neural network, you can create a new value and check if it's giving you the right value. So I'm going to ask you to perform 2 works. This is my last class. And I'm going to ask you to perform 2 works. In fact, I will put them in Ateneo. The first one is take this code and modify it to use a bias. A bias is a weight with input 1 always for each neuron. Yeah. So think how to manage to get the weights in the structure on the neural network. Think how to add all the weight of all the bias to all the structure of the neural network. This is my first work, and the second work is perform this with NumPy. Yeah, all this k, and so on may be done with NumPy in a much more easy way. So translate this code to NumPy to see how it works. Yeah, I don't care if the learning is well done. I don't care. I will just care on the structure and the operations. Yeah, I don't care anything else. I want you to think on NumPy to perform these operations. So there are two deliveries. The first one is modify this code to add the bias for each neuron, and the second one is translate this to NumPy. And I will give you, for the first one, I will give you 2 weeks, and for the second one, 4 weeks. Yeah. So that's it. I hope all you are okay, and I hope see you all you on coming back. Bye.